Bismillahirrahmanirrahim. Assalamu alaikum, everyone, and a very good afternoon. I'm Jawad Hashim, and I'm from the College of Medicine. I'd like to welcome you all to this workshop on formatting the results of statistical analysis and research writing. It's good to see all of you today, especially our graduate students. I always enjoy talking to you guys and sharing some of my knowledge and experience so that you can work better and more effectively in your starting careers in research. It's always interesting and exciting when you're talking at a higher level with graduate students. Most of my time, I'm of course teaching undergraduate students, and it's a different level of conversation with our graduate students, and it's certainly more problem solving and goal-directed conversations. So again, welcome to this workshop on formatting research results. These are our learning objectives, and I don't have any conflicts of interest to declare. So I've divided my presentation into three parts. The first part, I'll be talking about how to format statistics like t-tests, chi-square, ANOVA results. In the second part, we'll take a look at how to format tables, especially the statistical presentation of tables. And in the third part, we'll touch base on graphs and charts in research. So how do you present statistical results in graphs? So let's start with the first part, statistics. Typically, when you're writing a research article or a thesis, you have a results section in which you present most of your statistical results. And you can divide that results section into, say, 4 paragraphs. The first paragraph would be the number of study participants, or your whatever your unit of study is. It could be a study participant, it could be lab animals. You provide some demographics, summary, and some details in table 1. So it's a combination of text and tables, usually as a baseline. You don't want to replicate the entire table, but highlight the salient points in the first paragraph of the baseline characteristics. In paragraph 2, we discuss main findings related to the primary outcome and the study aim. So if you have a main hypothesis of the study, this is usually where you present it. And usually you have a table 2 and a figure 1. In which you would, yes, we will share the presentation after the workshop. So, and in subsequent paragraphs, you would have secondary outcome variables, including negative and inconclusive results, things that you don't want to highlight, but you still want to mention. Some of the exploratory analyses, which are not part of your primary objective of the study or the primary outcome, you can present that in the subsequent paragraph. And then finally, some additional results based on minor outcomes. So you can divide your approach to statistical analysis into 3 steps. The first step being descriptive analysis, and this is usually the mean and standard deviation. If your study data is not normally distributed, it has a lot of skew, then you may want to go with median and interquartile range. You would include some histograms and graphs. So these are just basic descriptive presentation of your data. And the second level would be the bivariate analysis, in which you would present correlation between 2 variables. You would analyze 2 variables against each other, so using a t-test, or multiple variables using ANOVA. And the graphs at this level are basically scatter plots comparing 2 variables, how they are related. And at the third level, you would do a multivariate analysis in which you have 1 outcome variable and multiple predictor variables. So you would do maybe a linear regression or a logistic regression in which the outcome is binary. So Or you could do a Poisson regression in which you have incident or number of events occurring in different groups. So these are the three major multivariate analysis approaches, which are called the canonical multivariate analyses. As an overview, this is the three levels of statistical analysis in a quantitative study that you are expected to present in a thesis or a research article. So I've chosen a sample article. This is not my article, just something I took that looked interesting and is gaining some media attention also. It's an article that describes the use of social media among young adults. It has a fairly large sample population, so it's about more than 23,000 respondents. And as you can imagine, this can only happen if you're doing an internet-based survey. It was not a face-to-face questionnaire or interviews. So big sample size, but on the other hand, you have to take the conclusions with a pinch of salt because it is an internet-based research, and the reliability of responses cannot be guaranteed. It is from Norway and has some interesting findings that I'll share with you. What I liked about this study is that it has a very well organized presentation. So if you look at the PDF file here and the headings within the PDF file, you can see that the introduction is nicely divided into subheadings, including the major areas of investigation, as well as a final paragraph, the present study. And then the materials and methods are divided neatly into the procedure, the study design, the participant, the questionnaire, and the statistical analysis. And similarly, in the results, they provide three sections. The group differences, which are the bivariate analysis, actually. So they've presented the bivariate analysis initially, and then they have presented the descriptive data after that. So this is, they've reversed the sequence. Usually you would present the descriptive data initially, and then the bivariate analysis or the group differences. And finally, they do the regression analysis, which is the third step, as I mentioned. So let's take a look. So this is from the results paragraph, and they've presented the group differences, which are the differences between various groups of interest, such as males versus females, students versus non-students, etc. And here you can see that they have started with the test, the name of a statistical test. They use, they refer to the table 1 initially. They refer to the p-value, which is the significance level, in a lowercase italic font. They have not provided the exact value. This is most likely because this is such a big study with 23,000 people. Any kind of statistical test you do with a very large sample, you're likely to get a positive or a significant result. So the p-value is very, very low. There is a leading zero just before the decimal point, and we'll talk a little bit more about that. There is the F value of the ANOVA test. This I see more commonly in social sciences as opposed to biomedical or engineering. So in psychology, sociology, education, you would see researchers presenting the intermediate statistics, such as the F value and not just the P value. And then we have the effect size. Effect size actually indicates how big the difference was, and this is again more commonly presented in psychology and social sciences. And then to help the reader, they provide an overall interpretation. Generally, the interpretation is given in the discussion section, not in the results. But to give some interpretation of the numbers, which may not, some readers may not be able to interpret the effect size using eta squared. They may not be aware of what is a small effect, what is a large effect. So the authors have actually presented an overall interpretation of the effect size, which is helpful. So this is, in a way, a model presentation of statistical data in the first paragraph of the results section. Something you could do well to emulate, especially if you're in a social sciences field. Notice that they have used a semicolon to separate this long sentence into parts, because they have used a comma to separate the different statistical parts in the parentheses. So again, attention to this level of detail is important. Notice also they have used a space around the equal to sign. So another example of presenting ANOVA results or a statistics result, you can see some of the things that they are, usually these values are set in parentheses. They use an uppercase letter for F for the ANOVA statistic, lowercase for P, italicized letters F and P. The degrees of freedom, which is 1 and 9, are presented as subscript, not italicized. There is no space falling between in the degrees of freedom. The F statistic is rounded. Here we have 3 digits of precision. The F statistic is followed by a comma and a space, and then the p-value. There is space on both sides of the equals to sign. And the exact value of p is not reported if it is less than 0.001. And the p-value can be rounded up from this set of values. And again, we'll see some difference of opinion between statisticians and between journals in how they want you to present the p-value, whether there should be a leading 0 or not, which we saw in the last example. Statisticians would insist on no leading 0 because p cannot be 1. But many journals continue to use a leading 0. All right, so again, another example of moving from your statistical table to your result, how to write this result. Say you have done a study in which you have compared the educational achievement of 3 groups of children, and you have the score of the test result, and you found that the result was significant. The p-value was 0.02. And you want to report this. How would you write this up? So a good way to write this would be to say that a one-way ANOVA was performed to compare the effect of 3 different studying techniques in exam score. And that your one-way ANOVA revealed that there was a statistically significant difference in mean exam score between at least 2 groups. So you don't know which 2 groups were different based on the ANOVA. The ANOVA just tells you that the groups are different. Which one of the 3 groups was higher or lower, the ANOVA will not tell you that. And here again, you can see that the F statistic is reported with 2,27, which is 2 is the between groups difference. You can see it over here. And 27 is the within groups difference. So most likely this study had 30 students, and the degree of freedom is usually n-1. And there were 3 groups, so the degree of freedom is 2, which is 3 groups minus 1. So those are the numbers you report after the letter F. And then the actual F value from your statistical output, and then the p-value, which is 0.02. The next step in ANOVA with multiple groups, you would do what's called a post-hoc analysis, and you can use any of the techniques that you are comfortable with or is familiar to you. For example, you could use two-key HSD, you could use Bonferroni correction. So there are multiple ways to do these post-hoc tests, and these are called multiple comparisons because you have three groups and you're now comparing each group with the other group. So you have multiple comparisons to do. And here you can see that if you look at the p-values or the significance levels, you can see here that between group 1 and 2, there is a significant difference. The scores, there's a difference of 7.7 in the mean score between group 1 and group 2. And that has been labeled as statistically significant by the two-key HSD post comparison. And you can report this as a positive finding in your study like this. The two-key HSD test for multiple comparisons found that the mean value of the exam score was significantly different between technique 1 and technique 2, and you present the p-value and the confidence interval for the mean difference. The mean difference, as we stated, was 7.7, but it can be anywhere from 0.9 to 14. So the 95% confidence interval is very close to 0. So it is possible that there was no difference, but the mean was 7.7, and you can call this statistically significant difference, and you can tentatively generate conclusions from this. Whereas there was no statistically significant difference between other groups. So, groups like group 2 and 3, there was no statistically significant difference. This is how you would present your ANOVA results in a text format in a study, making sure that you present p-values as well as maybe the f-value if your journal requires it, as well as a 95% confidence interval for the difference in means. So if the difference in means includes the value 0, if the confidence interval includes 0, that means it is possible that the two groups were not different, and the p-value will be more than 0.05. So the second stage, first stage is descriptive data, and in this study, they present this in the second paragraph of results instead of the first paragraph. But this is the descriptive analysis, and the descriptive data provides the means and some of the correlations. So they refer to the table, they refer to the primary outcome, and show that it was had moderate asymmetric distribution, so it was not totally normally distributed. They provide correlation coefficient, which is, you could say it is a descriptive statistic, but it is really a bivariate statistic. And it is nice to see that they have also provided some interpretation of the statistic itself. So generally, some statisticians don't like to have significance level for correlation coefficients because you have to interpret them subjectively. A correlation coefficient of less than 3 is most likely not very important. A correlation coefficient between 0.4 to 0.5 is moderate, and anything more than 0.6 is a strong correlation. So it has to be interpreted subjectively, but sometimes some readers are not familiar with that, and it's nice to include some kind of interpretation in your study results. So the important goals are in statistical presentation are clarity and accuracy. You have to be clear. You don't want to be too cluttered and overwhelm the reader, but you need to include all the important details that journal editors require based on their standards. So it is important to match the formatting style, and the best way to do is to look at the recent journal article very closely. You want to follow every single detail from a recently published article in that journal. You don't just follow the author guidelines, but sometimes the author guidelines are not updated, or the journal editor may have changed their mind about something. So the best way to look for that is to look at the most recent, which may be even online first article, not even published in the print journal. So some other useful tips on formatting your study results. Do not reduce your p-values to NS or non-significant. You want to provide the exact value. Do not include p-values in table 1. Table 1 is usually your baseline description of the study participants. So that's not where you do analysis, but again, we'll see some exceptions to that. Do not provide test statistics such as the F statistic. Again, difference of opinion between different fields and editors and journals. So in psychology journals, you'll see F statistic presented commonly, whereas in biomedical journals, you will not see that. So again, this is from a statistical statistician, and what they're saying may or may not apply to your field. P-values, usually 2 digits of precision are fine. Sometimes I've seen 3 digits. Some people prefer the point estimate and the confidence interval, the 95% confidence interval, as opposed to the p-value. And the means, again, should be presented with their 95% confidence interval for the difference. So these confidence intervals are for the outcome variables, not for your baseline variables. So baseline variables such as age, gender, income, education status, you don't need to present the 95% confidence interval. You probably present this standard deviation. But your outcome variables such as a difference in mean, the change in weight, the improvement in scores, all those should include a 95% confidence interval. A little bit about decimal places. Decimal places are important in research. You can present some number to 1 decimal place, 2 decimal places, but any digits before the decimal places don't count. It could be 3 decimal places, but avoid putting too many zeros after the decimal place if you cannot justify that level of accuracy. So this will not look very professional if you provide too many decimal places which are not justified. Related to this, and more important than decimal places, are what's called digits of precision. They used to be called significant figures. Mathematicians still do that, but in statistics, significant is a special word, and we should not use the word significant with digits of precision. So all zeros before a non-zero digit are not counted. So this is only 1 digit of precision. This is also 1 digit of precision. This is 2 digits of precision because there are 2 numbers. This also is 2 digits of precision because there are only 2 digits in here. And again, this is also 12, but it has a 0 in front of it, which of course does not add any precision. But zeros after a non-zero digit are counted. So this is 2 digits of precision. This is 3 digits of precision. This is 4 digits of precision. And this is 6 digits of precision. And usually it's very difficult to justify more than 3 digits of precision in measurement. unless you are using very advanced instruments. So be careful and limit yourself to 2 to 3 digits of precision in most of your presentation. Otherwise, it will not look very professional. And it all depends on your measuring instruments. So if you're using a measuring instrument that provides only millimeter accuracy, you cannot have multiple decimal places or too many digits of precision in your results output. So here is an example of a table with too many digits of precision and too many decimal places. You can see this is not recommended. The other thing to point out here is that the sample size is pretty small, 6, and they've provided a percentage with a decimal place, so 3 digits of precision. Again, this is not recommended. So a proper way to do this is to limit your decimal places and digits of precision. And here you can see that the age has been rounded to just the whole number. And white cell counts are have been rounded to just 1 decimal place. And because of the small sample size, the number of participants is just presented as the group over total sample size rather than a percentage. So when you're presenting p-values, don't include too many zeros in the p-value. If it's very low, less than 0.0001, then just write it as p less than 0.0001. Don't include too many digits of precision. 2 is enough, so p is equal to 0.76, or p is equal to 0.035, or p equals 0.001. A special case, again, you can ignore this if it's too much to remember, is if the p is between 0.01 and 0.001. In which case you can use 3 digits of precision instead of 2. But it's okay to be between 2 and 3, or use 2 or 3 digits of precision. But more than that, it looks a little bit silly or unprofessional. Just a quick thing, revision about rounding. Check the digit just before the rounding position. If it is less than 4, then round down. If it is 5 or greater, then round up. So for example, this number, if it is rounded to 2 decimal places, you need to remove the 8. What will the 5 become? It will become a 6, so it will become 12.06. And again, and this number, if you want to round it to 2 decimal places up to the 5, what will happen to the 4? It will be removed and it will not change the 5. So it will remain as 12.05. And if it's 0.055, then it will round up. So it will become 12.06. And you only need to look at just the number right next to the rounding spot. So you don't have to look at the 9. You can just look at the 4 and then round it based on that. So this will round to 12.05, even though there's a 9, that will not change the 4. Another recommendation from statisticians is to avoid using the plus-minus sign. Instead, use a comma. So mean, comma, standard deviation. And avoid using a dash between numbers because that can be a negative sign. So use the word to. And again, both these rules are not observed by many journals. So you really need to look at the journal rather than what the statisticians are saying, because you want to follow the journal editor's recommendation. When presenting your abstract, try to include a little bit more detail than just the p-value. So some journals prefer the actual numbers in the abstract and not just the p-value. So here you can see some numbers with comparisons and means, as well as correlation coefficient, the R value. A question that I'm frequently asked is, what is the difference between standard error and standard deviation? Standard error shows accuracy in estimating the sample mean. So if you repeat your experiment or survey many times and you find the standard deviation of all the sample means, that will be the standard error. And it shows the accuracy in estimating the sample mean itself. Typically, I see this being used with lab measurements. So in graphs showing the mean value from different lab animals, you would include the standard error of mean. Whereas standard deviation shows the variability in data values around the mean. So it's used for describing the sample. So whether the sample is spread out or not. And then don't forget 95% confidence interval. It shows the spread of data, and it is actually an inferential number, and it is used for outcome variables like the difference of means or your calculated number or some other kind of primary outcome measure that you were trying to measure and compare between different groups. So if the data is skewed, use the median interquartile range instead of the mean and standard deviation. If it's a minor skew, I would still continue to use the standard deviation and the mean. Remember that standard deviation includes only 68%. So if you typically presenting the two standard deviations, that includes 95% of the population. And the small standard deviation includes a tightly distributed population. A large standard deviation number means that the values are spread out. And the standard error is calculated using the standard deviation. The top symbol here, this is sigma. It's a Greek letter sigma for standard deviation. And n is the sample size. So as the sample size increases, your standard error, becomes closer to the standard deviation, and it becomes small. It becomes smaller and smaller, and so it shows accuracy more accurate. So if you have a large sample, your standard error will be smaller. Finally, regression analysis. You want to generally, regression analysis, we present it as text, not as table, but here in this study, they are providing a table, which I will show you. You still have to describe your standard, your regression analysis, including the amount of variance. This number, 11.9, is your R squared, or the adjusted R squared. They present it as a percentage to show it if it's bigger, but actually it's presented as 0.119. Showing it as a percentage makes it look bigger. But this is not a very good model. Typically, a good model would explain more of the variance in the outcome variable. Include which two variables are good predictors, which are not good predictors. You mentioned the effect size and hope some little bit of interpretation of the effect size, and some highlights of the model, that which variables were more important. So again, that's how you would present your regression analysis or a multivariate analysis. There's a second paragraph on multivariate analysis, and in this, they provide a summary. And again, variables that were good predictors, and how well did they here. The adjusted R-square is 0.175. Again, nothing very earth-shattering. This is a small number, but again, it's they've presented this nicely, and the entire paper is very well written, and it has gotten into a good journal. But as the results show, it is not very impressive. So some tips on statistical results presentation. You should specify your experimental unit, whether it was a person, lab animal, cell, or whether it was a student or the school, whether you looked at schools per se or students within schools. You should do a sample size calculation. I can do a workshop on sample size calculation if you'd like. Missing data should be mentioned usually at the end of the method section. You can mention missing data. Subjective assessments, if the assessments were subjective by the researcher, then you should mention whether there was blinding or not, whether the researcher was blind to whether the subject was in the control group or the experimental group. You should mention your statistical tests used with each p-value. This again, not everyone does that, but it's a good idea. Don't use a basic t-test if it is a before-after experiment. Then you have to use a paired t-test. And if the data are normally distributed, then you should use parametric test, the standard statistical test. But if the data are skewed, then you should use non-parametric tests. This is standard teaching, but if you have a large sample, more than 20 or more than 200, then you can just go directly to parametric tests because they can handle a little bit of skew and they are robust to that. Again, avoid too many statistical tests. Don't report a lot of p-values. That looks unprofessional to statisticians. However, we still continue to see that, and a lot of journal editors like that. They like to see a lot of statistical analysis. So again, you will have to be careful and see what you're doing. Don't stay in the middle ground. Don't do too many statistical tests, a lot of t-tests. That looks like that you are fishing for a positive result, a significant result. This is a statistical analysis paragraph from the methods section from Nature. So this is a very recent article just last week. And they look at the statistical analysis. It is extremely basic. There is nothing fancy here. Not even multivariate regression analysis. So the focus to get into Nature is not on fancy statistical tests, but rather on good study design and excellent methods and data collection. In fact, if you read Nature papers, you will see that p-values and statistical tests are not even mentioned in the results section. There is no mention of any p-values in the results section. So it is all about the study methods and the overall results. And similarly here, this is a research article from a top engineering journal. And even though they have done multiple measurements, they have calculated average, but there is no statistical analysis. There's not a single p-value or a statistical test in this top journal. They don't even show error bars or standard error of measurement, no standard deviations. And it is not for lack of knowledge. I think again, it is the way things are done in different fields. And the focus is on accuracy of measurement and replication in other studies rather than statistical analysis. So again, look at the journal in your field and see how they're doing. This is from New England Journal of Medicine, one of the top journals in clinical medicine. And again, here you can see very basic presentation of results. This is again a very recent article from this week's journal. And even with percentages, they don't mention the numbers. And the data analysis is very basic, confidence intervals and p-values. You can see that in this odds ratio, the confidence interval includes the number 0. The number 1, I'm sorry. So that means this confidence interval overlaps with the no effect. And that's why the p-value is 0.07. It is a non-significant. Whereas the second odds ratio has a confidence interval which does not cross 1. And here the p-value is less than 0.05. So again, very basic analysis in a top journal, but with excellent methods and carefully conducted experiments. So some common mistakes that we see and the peer reviewers pick up and the journal editors get irritated with the statistical presentation is that normality is not tested and statistical test is used without the distribution. So just plot the graph and see if it is approximately normally distributed. There are some special tests for normality. You can do that easily in SPSS or Jamovi. But if you present that, it's a nice way to show that you know what you're doing. And as I mentioned, paired statistical tests, if they're not used with before-after experiments, repeated measurements, that is a big no-no, and it shows that you're considering these as independent observations, whereas these are dependent observations. Chi-square test is used if the numbers are very low in some of the cells, like 0, 1, or 2, then you should not use chi-square test. You should use a non-parametric test. And Pearson coefficient is calculated even if one variable is measured using an ordinal scale, like a Likert scale. So people continue to do that. I see that in published articles also. Maybe you can get away with it, or if there's a statistician in the peer reviewers, they will pick this up. But generally, a Pearson's coefficient is fairly robust to minor deviations from normal distribution, and you should use it as it is more powerful than the non-parametric Spearman coefficient. And the difference between 3 or more groups are tested with t-test. I see this commonly, people doing multiple t-tests between different groups. If they have 5 groups, they will do, like 20 t-tests. That's not the way to go. As I showed you in the first article, you do an ANOVA and then do a post-hoc comparison, multiple comparison test. Again, how you write it is also very important. Your choice of words, how you phrase it. Here, we use words like increased. It implies a causal relationship. It's better to say that there was an association or something was higher or lower. Okay, so quiz time. I'd like you guys to see if you can write in the message box, what do you see the error in this statement? Good, but again, I'll tell you P can be written capital and non-italics in some journals. So unfortunately, the final word is still open. I agree. I prefer T to be small and italic, but it is not. That's not the error. But that's a good point. Anybody else or any other problem do you see in the statement? What's Is the conclusion justified?
I think that the p-value is high. It's more than 0.05.
Good,
And
excellent.
they concluded.
Yeah, actually, I prefer if you write it in the chat box because this is being recorded and it will be used as a YouTube presentation. So better if you can just type it in the chat box. So yeah, so the p-value is more than 0.05, and then it's not possible to make this kind of conclusion. What about this one? What's the problem here?
Sorry, can I just ask a question regarding the first statement?
Please, actually, please type your question. Don't use voice.
Okay, fine.
Yeah. What do you think of this statement? Is there any error in this? Detail is okay. Actually, the level of detail we expect is high in scientific writing, and if it's in your field, you will have no difficulty reading this. Semicolon could be used somewhere. That I agree with that. That's fine. But what about the p-value? Too high. Very good, Sanabi. So yeah, this is in the second part, the p-value is 0.06. So then you cannot use things like we're consistently greater because this is very much due to chance. It is very much possible that this is a random variation. What about this one? Here it is inappropriate wording, quite exactly, not quite significant. It's like, somebody's desperate to get published and they have results, and if you see a p-value of 0.05, all you can do is cry and repeat your experiment with the better methods or more accurate measurements. But you cannot report this as not quite significant. It's just not scientific. What about this? Yes, Anabil, that leaning towards significance, again, that is wishful thinking. And you should not, and actually you're not supposed to write like that. What you can write is the mean was higher in one group, however the difference was not statistically significant. So again, inappropriate wording, marginally but not significantly. That is not acceptable. And if there is a statistician in the peer review team, they will just shoot it down. So again, the p-value is more than 0.05. So hopefully you will not make these basic mistakes in your statistical presentation, in your theses and research articles. Okay, time for a break. We're going to take a vacation to Maldives. So this is a vacation I took before COVID, so no masks. And it's not a very long flight from Dubai via Emirates or United Etihad. And so some pictures from my vacation, just a visual break for you guys. So after you land at the airport, you have to take a seaplane. And you can see that the captain is not wearing any shoes. but it's a nice seaplane ride to the island where your hotel is. And this was the hotel or resort where I stayed. So it's a very nice place to visit with the beautiful sea, the turquoise blue color, and just the green sky. And from my room. So something you can look forward to after defending your thesis. Of course, beautiful sunsets. All right, back to the presentation. So we are now, and we've discussed statistics, and I'll quickly go over tables and graphs. I'm just going to discuss the statistical aspect of tables and graphs, not the overall presentation. So this is from the study that we presented initially about social media addiction, and they said if you're a woman, you're single, and have low income, then you're more likely to be addicted to social media. And here, this is how they present their table one. What you'll notice is that they have presented statistical results, including the F value. Again, very unusual for biomedical research to present F values, but you can present P values. Of course, all the P values are less than 0.001 because this is such a huge sample of 23,000. But so all the P values are significant. So it is important that they present the effect size and the eta squared. And again, they have to show to some readers who don't know how to interpret eta squared, what is the meaning of 0.068 or 0.012. Notice that they have provided the n and the percentage. The percentage is to 1 decimal place. The big message here is do not copy paste the output of a statistical program. You should write each value, type it in yourself. So you should have two windows side by side, and in your Word document, you should be typing each value or copy pasting each value one by one, because the statistical programs will not give you this kind of an exact output. It's usually in a completely different format, so it's best if it'll take some time, but it's worth it, and it shows that to the editor that you are hardworking, you're careful about details, and you have not wasted the editor's time by just sending the output of statistical program. Notice that they have presented the primary outcome measure in the table one. This is again very unusual for biomedical journals, but in psychology, I guess that that's something maybe expected to have the primary outcome measure for each of the groups that you're looking at. Table 2, they have presented the correlations. Again, this is very unusual for biomedical journals to present correlation coefficients like this. This is how it comes out in a statistics program, but it's not recommended. I would present, because it's just 3 numbers, I present this in the text. My feeling is they wanted to highlight this result and probably did not have a lot of other data to present. I was feeling multiple papers were written from the same data set. And so in this study or this paper, they just picked these 3 variables and did the correlations, and they've been able to write up a very decent paper with just 3 variables and have it published. So presentation is important. And this is their table 3 with regression analysis. Again, I don't recommend putting regression analysis in table. It should be in the text of the results section, in the last part of the results section. But again, I think they were desperate to put in some more, hard data in the paper. and look at, it's a lot of statistical output, which generally is not, you will not see in most research articles. Again, you have to use your judgment call, see what people are doing in the journal and in your field. So they've put not one model, but two models. The second step or second model includes the two special variables that they tested, narcissism and self-esteem. And you can see that, these were statistically significant, but the coefficients are small. So the effect of these variables on addiction is very small. And this does not come out directly until you read the whole paper. So again, the way they've highlighted it, it looks like it's a major result, but actually in reality, the effect is very tiny. And they've been able to get a paper out of this. One resource I want to share that I like is for students who don't have a hard time interpreting statistics is this statology.org. And it is useful. Let me speak up. I know it has an echo. I've tested it. Unfortunately, it is not going away. I tested it before this presentation. Sorry about that. I'll speak a little bit slower and louder. I hope that will be helpful. And so this is a useful website that you can, learn about statistics and basic statistical analysis. It has some tutorials as well as online calculators. Okay, another example of flawed and correct presentation in a table of statistical results is that we want to provide the actual value and the 95% confidence interval, as well as the p-value. So the exact p-value and not just, less significant or non-significant. This is a table from New England Journal of Medicine, and it shows table 1, the baseline demographic characteristics. Notice that they have used the plus-minus sign, which is not recommended. It should be a comma generally, but again, you have to look at your journal style and see what they want. And again, they have mixed the mean standard deviation with the number percentage in the same table. Again, you can get away with it if you are careful and show it clearly. But generally, what I prefer is in one table to have only either mean and standard deviation, or the number and percentage. So again, and the important thing here I want to show you is that this is a very clean presentation. It shows a very descriptive table title. It has the study groups in 4 columns as well as a total group. The order of study groups, they've started with the placebo and then the active groups and then the total group. And they've divided some of the rows into categories using an indent. To do an indent within a table, you cannot just press the tab key. You have to press the control tab. So hold down the control key and then press the tab, and then you can do an indent within Microsoft Word table. Okay, finally, we are in the graphs section. And again, we'll focus on the statistical presentation within graphs, not just graphs generally. This is just one figure from a large basic sciences article. And this one figure is divided into 5 panels. So again, there are multiple figures like this with multiple panels. And again, very compact, data-rich, and intense presentation of figures, charts, pictures. Again, this shows that you are doing a lot of work. It also shows that you are have a lot to say and a lot of attention to detail. So if you want to go and aim for a high impact journal, one of the top journals, you have to present in a information rich or a dense format rather than, this could have been 5 figures, but then you would not be able to show that you did a lot of work. What I want to highlight is that people are still doing a lot of multiple comparisons. These are t-tests between different groups and highlighted with stars. Again, statisticians don't like it, but journal editors in many of the basic science fields are still comfortable with it. This is what they're used to. This is what they did when they were students. So this is pretty much what you should be doing. Doing multiple comparisons with t-tests with different groups. Unfortunately, it will not make the statisticians happy, but that's the current standard in basic sciences. Again, you can see multiple comparisons, no p-values provided, just the asterisk sign, and very basic data analysis, statistical analysis, but right there in the top journal, top 1% in basic sciences. This is from agriculture, and again, you can see again reliance on t-tests, multiple comparisons without any adjustment or correction, no post-hoc testing, no ANOVA, but in the top journal. And again, you have to see what the journals are doing, what the recent authors are doing. Focus on good study design, good sample size, accurate measurements. A statistical analysis will not rescue a poorly conducted study. However, this is from medicine. This is from the New England Journal of Medicine article that I showed you earlier. This is a very recent, last week's. Again, notice the presentation is very clean. This is different from the basic sciences with multiple panels and congested presentation. So there's a descriptive title, and there's a dashed line and shading, which helps the reader understand how the study was conducted. The group names are near the lines and not in a separate legend, so very intuitive to read. And neatly labeled axes, and there are no grid lines in the chart. The chart itself has no grid lines. It is just a plain white field. One resource that I want to end up with is Equator Network. This is a website that has a lot of guidelines for reporting. It has, if you search for a statistic, then you get these 2 important, and the second one is the sample guidelines. These are basic statistical reporting guidelines for biomedical journals. And I'll show you 2 pages from this guideline. It is a very short guideline, but worth going over. This is the first page, and some of this we have already gone over. So don't report unnecessary level of decimal places. So you should be rounding your numbers. You should report both the total sample and the group sizes for each group. For percentages, as I showed you earlier, don't just write a percentage with a decimal place, but also include the numerator and denominator. You should summarize data that are non-normally distributed with medians. And generally, statisticians don't like standard error of mean. But in basic sciences, I see that frequently reported. So again, see which journal you're applying to. And then reporting statistical tests, you should, as I've mentioned, discussed previously, you should identify your variables, summarize, you do the basic descriptive summary, descriptive statistics. You should identify the test used, and you should use for paired tests before after studies. Then you need to do the repeated ANOVA. And again, they don't like using standard error of mean. They prefer to use a 95% confidence interval. P-values, again, we discussed this earlier. You should report the exact p-value and not just write p as non-significant. And if you're doing multiple statistical comparisons, you have to justify that using a post-hoc multiple comparison test like Bonferroni or Tukey. So that's the presentation, and this is our summary. We've gone over a lot. We've discussed statistics, the tables and the graphs. Let me pause and just take some questions. I see a couple of questions. Why grid lines are not preferred? Grid lines are what we call chart clutter or chart gunk. They are distracting. So you want a clean presentation in which you see the charts are being used to see trends, not to get the numerical value. So none of your readers will put a ruler and get a numerical value from the chart. If they need to do that, you should present that data in a table. For choosing a statistical test, you can go ahead and use Statology. There are some sites, again, maybe we can do a workshop on that, or if I find something, I can send it via graduate college email. Any other questions or comments? Anything that did not match with what you are doing in your field? Something that is done differently? Any other questions or comments? Can you repeat your questions, Zed? Just type it in. Because I minimized the chat box towards the end. Okay, so the question is, for statement one, can you say it is higher with a difference that is not significant? That is not accurate. It is not higher. It is the same from the statistical analysis. There is no difference. Actually, the formal wording is we failed to reject the null hypothesis, or we reject the null hypothesis. Those are the two options. So it's not possible. If it is not significant, all you can say is the differences were not significant, even though there is a difference in means. If the difference in two groups is big, the number difference is big, and still it is statistically non-significant, most likely your sample size is too small, or the data is very variable. The standard deviations are too high. Yeah, why grid lines are not preferred? It's too much clutter in the chart. your chart will look very busy. Without the grid lines, it looks cleaner and less cluttered. One compromise is to provide very few grid lines in a very light gray color. So instead of providing, if you have 0 to 100, instead of providing 10 grid lines, you just provide 3 grid lines, 25, 50, and 75, and in very light gray color, and just the horizontal ones, not the vertical ones. So, or the opposite. So just very few grid lines in a very light color that does not distract from the overall message of the chart. Yeah, I answered this question earlier, that this is a separate workshop, choosing the right statistical test. I actually offered that workshop. I think the response from graduate college was that people are more interested in the formatting of the results. As I mentioned in some of the engineering papers, there are no statistical tests done. So, again, focus more on your study design and careful collection of data, good instruments, calibration, using controls.
Yeah, Mr. Jawad, allow me just to open the mic because I have one comment and one question, and I
Sure.
Yeah.
Yeah, that's okay. Now we're done with the.
Yeah, thank you very much. The first one, that I am from the IT college, and
Okay.
we have a complete discipline that is called computational neural science, where we do experiments that combines the characteristics of human brain with some tools from the computer. And when we present our results, we do care about the statistical tests.
Good.
Yeah, this is one thing. So I would be thankful if you can share a recording of that workshop about choosing the statistical test, or if you can conduct it
Okay.
some way in the coming.
I can contact graduate college and see. Yeah, sure.
Yeah.
Anytime you're doing multiple measurements in the same animal, same model, you should do a statistical analysis.
Yeah.
Because you have to average, you have to get the mean, and you have to compare the means between different groups. So that is important.
Yeah, my question is, I had a recent experiment where I have three-way repeated measure ANOVA because I have 3 independent variables.
Okay.
And those variables are 2 to 12, which resulted into 48 different
groups, comparisons.
Groups. Yeah, and the subjects are the same. All the subjects, they sat on all of those 48 experiments. So I did my research, then I decided that maybe 3-way repeated measure ANOVA is good for this kind of to represent my results, and then I make the pairwise comparison to represent the differences between those numbers. The issue is that I have lots of numbers and the pairs of comparison that makes the results write up very lengthy. It's about like 7 pages.
Yeah.
So what I did, I summarized the results in tables. Then wherever the difference is significant, I make it bold and italic. Other numbers are not bold and italic. So I know that it is a practice, it is a convention that whenever you have significant difference, you need to report the p-value. But in the way that I summarized the data, I cannot report the p-value. I only report whether it is significant or not significant by making the number bold and italic. I wrote it under the table for sure. So my question is this acceptable if because I haven't sent it for publication yet, so I need to know how can I tackle such an issue?
The short answer is check with the recent article in that journal. So if the journals are okay with that, as a statistician, that is not recommended. You know, if there is a statistician and a peer reviewer, they will not like it. So, but
The write-up, sorry, so
go ahead.
just to add, this could be important. Yani will allow you to give crisper answer. The write-up with all of those, the way that the convention statistician wrote those statements are in the supplementary materials with p-value, with the confidence interval, and all of those things.
Yeah. What I would recommend is, I think maybe we can discuss this later on because this is a very specific case.
Okay,
let me just end this with that select the important findings in the main article. So, and include the p-values in the main article. And findings that are not important are not related to the main study aim, that you should put in the supplementary.
I got that. Okay, makes sense. Thank you very much.
Again, if you have a lot of data statistics, you can shorten them by putting them in a table rather than in a text. Okay, I think we'll end now. Thank you very much. It's a pleasure to be